First problem I'm going to be looking at is this nitrogen problem. We have a water-cooled nuclear plant, and it says that the radiation decreases in such a way that the rate of change in radiation is directly proportional to the radiation level. The problem asks me to write a differential equation expressing that, and then it asks me to find a particular solution if, when it's shut down, the radiation level is 3 times 10 to the 17th units. After 60 seconds, it drops to 5.6 times 10 to the 13th units.
All right, I'm going to start out with the differential equation dr dt equals k times r. So that's the rate of change of the radiation is directly proportional to the amount of radiation. That's my equation there. I'm going to separate variables, get everything both on the same sides of the equation, multiply both sides by dt. So I'm going to have k dt over on one side of the equation. I'm going to have 1 over r dr over on the other side. I'll take the integral of both sides. That'll give me the natural log of the absolute value of r is equal to derivative of k with respect to t is kt. Somewhere I need to have a constant value. So I'm going to have kt plus c here, and I'm going to continue. At this point, I'm going to write this in log form. That's log base e. So that's e to the kt plus c power is equal to the absolute value of r. If I take out the absolute value, I can do a plus or minus e to the kt plus c. I can let some c naught equal plus or minus e to the c. And I can write r as c naught times e to the kt power. All right? Once I've got that set up, this is basically a PERT problem. I need to go back and I need to take those initial values and substitute those into the function. Okay? This is where things get a little bit more interesting. So I know that when time is equal to 0, that there are 3 times 10 to the 17th, whatever my units are here, units of radiation. So I can substitute that in here. That's going to be 3 times 10 to the 17th is equal to, that's going to be c naught times e to the kt times 0. Okay? Anything taken to the 0 power is 1. So this whole thing here is really just e to the 0, which just becomes 1. So that leaves me with 1 c naught equaling 3 times 10 to the 17th. Turns out 3 times 10 to the 17th was my initial value. All right? So I can substitute that into my original function. It's going to be 3 times 10 to the 17th e to the kt. All right? However, the two variables, I've got to solve for the k and I've got to solve for the c. I've got the c, so I'm going to go back. Now I know that after 60 seconds, after t is equal to 60, I know that there's a total of, I believe it's 5.6 times 10 to the 13th units of radiation remaining. All right? So once again, I'm going to substitute that into my equation over here. So I know that 5.6 times 10 to the 13th is going to equal 3 times 10 to the 17th e to the kt, and I can solve this equation. Divide both sides by 3 times 10 to the 17th. Okay, so that's going to be 5.6 times 10 to the 13th, and that's going to be divided by 3 times 10 to the 17th power. That's going to be approximately 0.000186 repeating equals e to the, and I need to watch it here, I forgot to substitute in my 60. I know that t is equal to 60. So that's e to the 60k power. I can now convert this in log form. It's going to be a log base e, so a natural log of this value right here. And again, better if you leave the original decimal in your calculator. And that's going to be equal to 60k. And so now I can run that on my calculator, take the natural log of that value, and I'm going to divide by 60. K is going to be approximately negative 0.1431, and that's going to be my missing K value. So my final equation here is going to be R equals 3 times 10 to the 17th times e to the negative 1.431 t ends up being my final equation.